Hi, good morning, everyone. Good morning. Right. Are there any questions from the last class? Any homework questions? Yes. What? What are the questions? Homework from we started with astrophysics last class, no? 46A and only. Right. 46. Where the satellites may be in an equatorial orbit or a polar orbit, as shown. Where the satellite in a polar orbit circles the Earth at a height of 8.5 into 10⁵ meters above the surface of the Earth. Show that the gravitational potential at this height is about this much. The mass of the Earth is given, the radius of the Earth is given. So the gravitational potential is given by minus G m over R minus, what is the value of G? 6.67 into 10 to the power minus 11. Mass of the Earth is 5.98 into 10 to the power 24. And the distance is going to be, we are looking at the radius of the Earth is 6,660 kilometers. And they are talking about a height of 8.5 into 10 to the power 5 meters above the surface of the Earth. So from the center of the Earth to this orbit is going to be 6,360 is going to be 6,360 into 10 to the power 3 in meters, the radius, plus the height above the surface is 8.5 into 10 to the power 5. That will be 7.21 into 10 to the power 6. So that's going to be 5.53 minus 5.53 into 10 to the power 7 joules per kilogram. That will be the gravitational potential at this point. Correct? Hence, calculate the increase in gravitational potential energy when the satellite is placed in orbit. Okay. Gravitational potential at the surface of the Earth is given. So when you lift it up, the change in the gravitational potential energy will be gravitational potential difference multiplied by the mass, right? Do you agree with me? Am I right? Correct. So if you want it like this, I can take is m into phi2 minus m into phi1. M into phi2 is the potential energy once you put it to the orbit, minus m into phi1 is the potential energy when it is on the surface of the Earth. So since m is common, if I take the m out, that is phi2 minus phi1. Agree? So m into that m is satellite mass is 4,990. Phi2, that means once you put to the orbit, the gravitational potential is minus 5.53 into 10 to the power 7 minus, when it is on the surface of the earth, it's minus 6.27 into 10 to the power 7. So minus minus will make it plus 6.27 into 10 to the power 7. So that's going to be 3.69 into 10 to the power 10 joules. Done. What's next? What's next? 50B. A satellite is launched from the surface of the Earth into an orbiter height 5 RE above the surface of the Earth. Okay. The change in gravitational potential energy of a mass m when it experiences a vertical displacement delta h can be calculated using the expression mg delta h. State why this expression cannot be used to calculate the change in gravitational potential energy of the satellite. So I told you the g doesn't remain the same when you go when you go that high above the surface of the Earth, g doesn't remain the same, so you can't use mg delta h. Okay. Calculate the change in gravitational potential energy of the satellite. Mass of the Earth is given. Mass of the satellite is given. What is meant by RE is given. So when it goes to the initial potential energy, now it goes from the surface of the Earth to an orbit above, a height 5 RE above the surface of the Earth. So its E1 is m into 5R. And G is given here in terms of RE. G is given in terms of RE. Right. How can we make use of that? Because you know, phi equals minus g mo r. Okay. Phi equals minus d mo r. And g equals g mo r square. Okay. G equals g mo r square. Am I right? So if I multiply both the sides with r, gr equals gm over r. Am I right? Which means phi equals minus, for gm over r I can write gr Agree? Right? So, initial potential energy when it is at the surface of the earth, if I take it as m into 5r, I can take it as m into minus g into, initially it is at a distance of re at the surface of the earth. So r will be re, correct? When it is at a point re, the value of g's we can see here. G is 9.8. So my g is 9.8. So it's going to be m into minus m into 9.8 into re. Listen carefully. E2, once you put it to the track, once you put it to the orbit, E2 is equal to m into 5.2. So that is m into, now the 5.2 I can write it as, using the same thing, minus whatever the g now, I'll take it as g2, into now the r is 6re. Do you agree with me? Now the object is at a height 5re above the surface of the earth. So with the radius of the surface earth re, the distance to the object will be now 6re. Am I right? Which is going to be minus m. Now what is the g2 from the graph? When it is at 6re, when it is at 6re, the g is, if I'm not mistaken, something slightly above 0.2. I believe I can take it as 0.3. No, 0.3 is, no, you know, 6re. 6re is here. So I think it is about 0.25 maybe. 0.25. That is the G2. Into 6re. So that is minus m. 0.25 into 6 is 1.5 re. This is the E2. So the change in gravitational potential energy is going to be E2 minus E1, final potential energy minus initial potential energy. Final potential energy E2 is minus 1.5 m re minus the initial potential energy is minus 9.8 m re. So minus minus will make it plus. So 9.8 MRE minus 1.5 MRE. 9.8 minus 1.5 is 8.3 MRE. That is 8.3. The M is the mass of the satellite, which is 3.5 into 10 to the power 3 into RE is 6.4 into 10 to the power 6. I'm getting 1.86 into 10 to the power 11. Totally fine as long as you are getting this answer. What is your answer? Okay, what about you? 1.75. Anyone else?
Excuse me, sir. So how do you get the 6re, sir?
6re is, now they are telling this object is taken to a height of 5re above the surface of the earth, right? Above the surface of the earth means from the center of the earth, the distance to the object is 6re, right? isn't it?
Mm. Mm.
I'm not telling this is the only way of doing it, but this is a very classy way of doing it. Huh? You can impress the examiner. But as long as you are getting anything around this, it should be fine. If you see in the whole process, I didn't use the mass of the earth. You used it. Okay. What's next? That's it. What is the last subtopic we have done? Gravitational potential energy. Did you all get the theory tube today? Did you all get a tube today? Right. Let's turn to page number 30, question number 17. Right. The escape velocity is the minimum speed needed for an object to escape the gravitational field of a planet. An object at the escape velocity has a kinetic energy equal to the magnitude of the gravitational potential energy of its gravitational potential energy at the surface of the planet. Show that escape velocity v for a planet of mass m and the radius r is given by this expression. Right. Let's listen. Whereas now there is something called an escape velocity. Now, when you throw an object, okay, why does it fall back to the earth? Because of the gravity. No? But the faster that you can throw, the further it goes, right? So if you can throw it faster, and if that speed is sufficient to go beyond this atmosphere of the earth, to go beyond the gravitational field of the earth, then it won't come back to the earth. Okay? It won't come back to the earth. That speed at which that you need to throw, the minimum speed that is required to do this, is what you call what velocity? Escape velocity. Okay? So for the earth, based on its radius and mass, we can find the escape velocity. And if you can throw someone at that speed, that person or the object will not come back to the earth again. Okay? So this question is about that. Show that the escape velocity v for a planet of mass m and radius r is given by this expression. So now let's say the mass is m. Mass of the planet is m. And you are throwing an object of mass simple m from the surface of this. Okay? And you want to throw this forever. What is that speed required? So the question says what? an object traveling at the escape velocity has a kinetic energy. It has a kinetic energy equal to the magnitude of its gravitational potential energy at the surface of the planet. So if it is given a speed of v, its kinetic energy is half mv square. Its potential energy is magnitude of the potential energy. They're talking about the magnitude of the potential energy, which is without the minus sign, g mm over r. Agree? R is the radius of the planet. M is the mass of the planet. Simple M is the mass of the object that you are throwing. So if you equate the two, simple limb here will cancel off with the simple limb here. Cross multiply, v square equals 2g m over r. So that means v equals square root of 2g m over r. So if a mass of m, there is a bit more physics involved in what they have told, which they haven't expected you to know. You really want me to explain it, okay? Not necessarily in the Excel syllabus. What really happens here is the total potential energy and the kinetic energy at this point becomes equal to the total potential energy and the kinetic energy at infinity. So the total potential energy at the surface is minus dmm over r over plus kinetic energy is half mv square. That is equal to the total kinetic energy at infinity is 0, total potential energy at infinity is 0. Then when you take this minus sign to the other side, it becomes half mv square. That is equal to, without the minus sign, gmm over r. This gmm over r is the magnitude of the potential energy. That is what they, without expecting you to do this, they straight away have given you that the kinetic energy is equal to the magnitude of the potential. Okay. Right, take it down. Right. Show that the escape velocity for a mass at the Earth's surface is about this much. Mass of the Earth is given, radius of the Earth is given. This is any baby can do. Just substitute into this equation. V equals square root of 2 into 6.67 into 10 to the power minus 11. Mass of the Earth is 5.98 into 10 to the power 24. The R is 6.36 into 10 to the power 6. Which is 1.12 into 10 to the power 4. That is the escape velocity. So that means which is about 11,200. If you can project something at a speed more than 11,200 meters per second, it will not come back to Earth. 11,200 meters per second. Okay. Right. The next part. When the Earth formed, okay, you know, Earth was formed, right? When? 4 billion years ago. 4 billion years ago. Yeah. So they are talking about that when the Earth formed, a large proportion of the gas in the Earth's atmosphere was hydrogen. In the Earth's atmosphere was hydrogen. Explain why hydrogen gas is no longer a large proportion of the gas in the Earth's atmosphere. No further calculations is necessary. At 20 degrees Celsius, the root mean square speed of hydrogen is given 1900 meters per second. 1900 meters per second. Can you give me an answer for that? Try to connect this with the previous part. Huh? Escape velocities. Okay, so guys, now did you realize in the previous part? Okay. V is equal to square root of 2g more r. So that escape velocity depends on the mass. Okay. Now the mass of the Earth has gone up to 5.98 into 10 to the power 24 kilograms. Now, Earth is a planet, right? Planet, right? How these planets are formed? Okay, what are the other planets? You know how many planets are there? Huh? In our solar system, I'm talking about Milky Way. Let's stick to Milky Way. In our galaxy, in our solar system, how many planets are there? 8. What are the 8 planets? Starting from? Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto? No. Why not? Then what is Pluto? It's a dwarf planet. What is a dwarf planet? Why it is not a planet? What is the difference between a planet and a dwarf planet? Haven't you all done this for levels? No. No. Okay. I don't know about those who did local O levels. But those who did Cambridge and Edexcel, definitely you have done, right? No? You did what? Cambridge? No. In the Cambridge syllabus, actually, they have included this in the new syllabus from last year. You all did O levels one before last. But Edexcel syllabus, it was anyway there. So those who did Edexcel O levels, definitely you have gone through it. So what makes it what the planets can attract the particles around it and attract the particles, and it can clear the area around it. The planets, what makes it a planet is in the space, it can attract the particles around it. Its gravitational field is sufficient to attract the particles and make a sphere. Okay, it can make a sphere by clearing anything around it. Its gravitational field is strong enough. But it doesn't work with a dwarf planet. The dwarf planet doesn't have a sufficient gravitational field to clear the area around it. So anyway, so how this Earth formed was by clearing the particles around it, by attracting the particles, everything that was around the Earth. So initially when Earth started, it was a small one. It didn't have much mass. Okay, the mass was less. So the mass was less means the escape velocity is also less. So now according to our calculation, 11,000 meters per second came in the previous part with the current mass of the Earth. No? So if you see the initial, very beginning at the early stage, the mass would have been much, much lesser than this. So then the escape velocity is also less. Then the escape velocity would have been less than 1,900 meters per second, which is the speed of the hydrogen atom they have given at 20 degrees Celsius. So hydrogen would have escaped from this Earth's atmosphere. Understood? Yes. Yeah. Sorry, mass. Now, what they are telling here is explain why when the Earth formed, the Earth formed in the sense what I understand by the Earth formed is the initial stage of Earth form. Then with time, Earth got bigger. Okay, you get it? So write the answer. Initially, when the Earth was formed, its mass was lesser. And escape velocity would have been less than 1,900 meters per second. Okay, that's enough for a 2 mark. Temperature of the Earth has been rising because of change in velocity. Yeah, I thought about that point as well, but actually, no. Here the temperature they have given 20 degrees Celsius. No, 20 degrees Celsius means 293 Kelvin. No, so now let's say the temperature has gone up to 30 degrees Celsius, not even 30. If you take the average temperature, still around that area. Come on. Even if you consider it to be 30 degrees Celsius, 273 plus 30 is 303 Kelvin. So if you look at the thermodynamic temperature difference, 293 to 303 means it's a very small difference. In terms of percentage, I would say not even 3% or 3 to 4% increment. That won't make a big difference in the escape velocity. Okay. Right. Guys, page 36, question 21. In the 18th century, Cavendish carried out the first experiment to determine the gravitational constant. The experiment used two lead spheres. A physicist planned to investigate the gravitational force using lead spheres, identical to the ones used in Cavendish's original experiments. One of the spheres had a diameter of 30.5 centimeters and the mass of 158 kilograms. The second sphere had a diameter of 2.5 centimeters and a mass of 0.73 kilograms. The minimum force that could be measured by the physicist was 50 micronewtons. Deduce whether the physicist would be able to measure the gravitational force between the two spheres. Can you please? It's a very easy one. All you need to do is F equals GMMO R square. So these are the two spheres. One has a diameter of 30.5 centimeters, means the radius of half of that, 15.25 centimeters. The other one has a radius of 1.25 centimeters. this has a mass of 158 kilogram and this has a mass of 0.73 kilograms. So F equals 6.67 into 10 to the power minus 11 into the mass is 158 into 0.73. That's what is the R? What is the distance between the two objects? Addition of both. Now listen, why? Now guys, the experiment is to see whether he can measure the force, no? Deduce whether physics would be able to measure the gravitational force between the two spheres. So the force between them will be maximum when they are as close as possible, right? So when they are as close as possible means when they are touching each other. Am I right? So when the two objects are touching each other, the distance between them will be the distance between their center of masses, which is basically the addition of their radii, which is 15.25 plus 1.25, 16.5 in centimeters. So 16.5 centimeters will be 0.165 in meters, and that needs to be squared. Correct? That is 2.82, 2.83 into 10 to the power minus 7 in newtons. If I'm to get it in micronewtons, which is 10 to the power multiplied by 10 to the power 6, that is going to be 0.283 micronewtons is the theoretical value of the force. Am I right? So which means the minimum force that he can measure by whatever the gadget he has to measure the minimum force, the smallest force that he can measure is 50 micronewtons. Am I right? So do you think he can measure it? Whether physics would be able to measure the gravitational force between the two spheres, this is less than 50 micronewtons. So the conclusion is no, he cannot. That's easy 4 marks. Okay. Part B. That's another 2 easy marks. Experiments to determine G have usually been carried out using large masses. In 2021, physicists at the University of Vienna carried out an experiment to determine G using gold spheres with masses of less than 100 milligrams. They obtained a value of G equal to 6.04 into 10 to the power minus 11 in SI units. Show that this is a correct unit for G. Right, guys, here see F equals G m1 m2 over r square. Correct? In terms of units, force is newtons. G's unit is, if I take it like this, m1 m2 is kilograms into kilograms, or the r is meters, meter square. So if I get the unit of G subjected, that is going to be newtons into meter square over kilogram into kilogram is square kilograms. So what is newtons in terms of SI units? kg ms minus 2. If you can't remember, F equals ma, the most obvious thing to remember. F is force in newtons, m is mass in kilograms, a is acceleration in ms minus 2. So kilogram ms minus 2. So kg ms minus 2 into m square over kilogram square. Simple max. So guys, it will be kilogram divided by kilogram will be per kilogram. Meters into meter square will be meter cube. S minus 2 per kilogram. Done. right? The physicists concluded that their value for G was within reasonable agreement with the standard value of G. Evaluate the validity of their conclusion. The standard value of G is 6.67 into 10 to the power minus 11. The value they have calculated is 6.04 into 10 to the power minus 11. Let's see how much is the percentage difference. If that percentage difference is less than maybe about 10%, can agree. So guys, 6.67 into 10 to the power minus 11 minus 6.04 into 10 to the power minus 11 is the difference. That divided by the actual value is 6.67 into 10 to the power minus 11. That multiplied by 100 will give you by what percentage the calculated value is varying from the actual value. Correct? That's about 9.4%. I would say it's a good experiment. The can agree on the conclusion. And write a statement saying, yes, it is within a reasonable agreement with the standard value of G.
So can you tell the conclusion?
Sorry?
So the conclusion, can you get it again?
Yes, it is within a reasonable agreement with the standard value of G. Or you can just say, yes, it is a reasonable value. That's more than enough. So 2 mark anyway. Right, guys, turn to page number 45, question number 26. We already have done the A part. So I want to do the part 2. Read the question. The dwarf planet Ceres is the largest object in the asteroid belt. Ceres has a mass of 9.38 in 10 to the power 20 kilograms, and Ceres has a circular orbit of radius 4.14 into 10 to the power 11 meters around the sun. Show that the gravitational force exerted on Ceres by the sun is about seven seconds. Please stop your work and look at this. Okay. Guys, now this is the sun. This is the planet, the dwarf planet, which is orbiting the sun. We are going to find how long it takes for this orbit. Correct? How long it takes is the question. I'll take this radius to be r. Come on. Okay. We have to find this. So I'm going to use, look at this. So guys, it's orbiting, the planet is orbiting around the sun because of the gravitational force. Agree? Yes, right? So we are all orbiting around the sun because of the gravitational force. Sun has a huge gravitational force. No? So if you take all the other planets, moons, and everything put together in the solar system, and still everything together is still less than 1% of the mass of the sun. So mass of the sun is huge. So if I am not mistaken, the Earth is 10 to the power 24 kilograms. And the mass of the sun is about 10 to the power 31 kilograms. So which is about, the mass of the sun is 10 million times the mass of the sun. 10 million times. Okay, if you take 10 million Earths put together, is what going to be the mass of the sun. Okay, that massive. So obviously that has a massive gravitational field around it. So that gravitational field is what making all the planets orbit around it. Correct. So now, if I use F equals ma, look at this. If I use F equals ma for this planet, I'll take the mass of the sun to be m, mass of the planet to be simple m. F is going to be g mm over r square. M a is going to be r omega square. You remember this? Centripetal acceleration is r omega square. So one of these m's will cancel off. If you cross multiply, gm equals r into r square is r cube omega square. So gm equals r cube omega, I can write it as 2 pi over t, that square. So gm equals r cube 2 pi over t square is 4 pi square over t square. So now if I get the t square subjected, which is the time period, that is going to be 4 pi square r cube over g. So the t square will be, substitute 4 pi square. R is given, this has a circular orbit of radius 4.14 into 10 to the power 11. And that cube over g is 6.67 into 10 to the power minus 11 into the mass of the mass of the sun is given 1.99 into 10 to the power 30. Mass of the sun is 1.99 into 10 to the power 30. So this will give you the t square. So get that square root, that will be the t. That's going to be I'm getting 1.453 into 10 to the power 8 seconds. But they want it in years. No? So this is in seconds. Divide that by this one. We have 1 year is 3.15 into 10 to the power 7 seconds. Divide by 3.15 into 10 to the power 7, which gives you 4.61 years. Correct me if I'm wrong. This is the time taken for the planet Ceres, the dwarf planet Ceres, to go around the Earth. Take it down.
So why do you take the mass of the sun without any development?
Now, I have taken the mass of the sun to be capital M, mass of the dwarf planet to be simple M. So when I initially used the equation, GMM over R square, yeah, that is what accelerated. Sun is not accelerating. Sun is not accelerating. I used F equals ma for the planet. Right. Sun is not accelerating with respect to us, I'm saying. If you take at a universal level, even the sun is. Sun is accelerating because the universe is expanding. That is what we are going to speak next. The universe is expanding. Okay. Right. Right. There's the next one. Turn 2. Question number, page 53, question 31. Right. I'll do the part A1. You try the second one. The planets orbit the sun approximately circular orbits. The orbital time t of a planet is related to the average distance r of the planet from the sun. Show that the t is related to r by this expression. So once again, the same thing what I did in the previous question. The sun is here in the middle. So let's say there is a planet which is orbiting around the sun, and that has a mass of simple m. Sun's mass is capital M. The distance between the center of masses of them is simple r. Okay, so I'll begin with F equals ma. F is g mmr square. Simple m into a is r omega square. So the simple m will cancel off. Mass of the planet will cancel off. So that's going to be gm equals r into r square is r cubed. Omega square will be, omega is 2 pi over t, and that square. That is gm equals r cubed 4 pi square over t square. So if I cross multiply and get the t square subject, t square equals 4 pi square over G in into R cube. So now look at this, guys. Look at my argument. Whatever the planet that you take which is orbiting around the sun, whether it is Jupiter or Mars or Earth or whatever, Uranus or whatever, G is anyway a constant, M is anyway a constant, capital N here is the mass of the sun. So the mass, the central body, that is anyway constant for any planet that you apply here. So G is a constant, M is a constant, 4 pi square is anyway a constant. So which means this part is a constant. If that is a constant, that tells you what? T cube is proportional, sorry, T square is proportional to R cube. Correct. So basically, the time which is taken for a planet to go around the sun, one round, depends on the distance to it, or nothing else. Okay. So further a planet is, larger will be the time taken. Understand? Yes. So in the previous question that we did, the dwarf planet is, listen, we got the time period to be how much? 4 point some years now. What is the time period of the Earth? What is the value? 1 year. Time taken for the Earth to go around the sun is what we have taken as 1 year, right? 365.25 days. So guys, increasing distance from the sun, who is the first planet? Mercury and Venus and Earth and Mars and wait. Then this dwarf planet is where? In the asteroid belt. Where is the asteroid belt? Between Mars and Jupiter. Between Mars and Jupiter. Correct, right? Between Mars and Jupiter. So that means definitely the distance to that dwarf planet what we calculated in the previous question is more than the distance from the sun to the Earth. That is why it was more than 1 year we got. Understand? Right. So when you do a question, don't just do it and just throw it there. Try to get something from that and continue. That will make it easier for you to understand the questions better in the upcoming questions. Copy that one and try the next part. Shall I do it? How many more minutes you want? Okay, I'll give you 2 more minutes. Okay, let me do it. Guys, now look at the screen. Stop your work. Whatever the efforts that you have put, completely stop it. You can continue that method what you're trying to do later after class. Now look at what I'm doing. Okay. Now, if an object is moving in a circle, we have learned, okay, if it is moving at an angular speed of omega, okay, and guys, let's say it's moving a distance theta, angular displacement, angle theta, in a time t, that means theta is equal to omega into t. Am I right? Omega is the angular speed. What is the angle it travels in 1 second? So if it is traveling for a time t, the angle it's traveling, angle it's covering is theta equals omega into t. Okay. Now it's quite obvious. The Earth will complete 1 circle before Jupiter, right? Correct, no? Correct. So Jupiter, Earth's taking 12 months means the Earth, time period of the Earth is 12 months means that definitely the time period of Jupiter will be more than 12. That's correct, no? That's because t square is proportional to r cube. How bigger the r, bigger will be the t. So guys, now Earth will go and complete a circle. So when Earth is completing the circle here, the Jupiter may be somewhere here. Oh, I don't know. Somewhere, but still haven't completed the circle. Okay. So the question is, after how long a website states that the Jupiter, Earth and Jupiter are in opposition every 13 months. What is meant by opposition is Sun, Earth and Jupiter will be in the same line. Correct? So when Earth has traveled a certain distance, when it completes an Earth round, what is the angular displacement it's making? 2 pi, 360, we are in radians, 2 pi. So when they come to this, let's say they come here, they come in line at this point. The angular displacement is theta. Okay. Okay, first let me try to get the time period connection. T Earth square is proportional to twelve square is proportional to r cube. The mean distance of the Earth to Sun is 1.5 into 10 to the power 11 cube. And the T Jupiter, if I take it as Tj, Tj square will be proportional to the distance from Jupiter to Sun is 7.8 into 10 to the power 11. That cube. So by dividing these two, we will get Tj square divided by 12 square. That is 7.8 into 10 to the power 11 cube divided by 1.5 into 10 to the power 11 cube. From here, you can find the Tj. Is the Tj square, is the Tj 142.3 months? I'm getting 142.29. Huh? 142.3, right? Correct, no? I get in this one? That's too far, no? Hundred 42.3, right? Is that okay? Yes. So now listen to me. So guys, now Jupiter takes 142 odd months to make one complete circle. So which means Earth will go around this circle, and when it is in the second circle, only it will come and meet Jupiter, which is still in the first circle. Do you understand that simple thing? Now imagine in a much more understandable way, you're running a marathon, or let's say 5,000 meter race in Sugadadasa, where one round is 400 meters. So to run for 5,000 meters, you have to run 12.5 rounds. And you are running with a person who is extremely slower than you. Okay? You have run you have started, you both started at the same time at the same point. He's extremely slower than you. So you complete one round. And while you are in the second round, you will be meeting him again, right? He's still in the first round. Okay, that is a scenario here. Earth is traveling much faster than Jupiter. Okay, so Earth has completed the first round, and while Earth is in the second round, it's meeting Jupiter again, where the Jupiter is still in the first round. Do you understand that? Right. So that means, guys, theta equals omega t. No? Now, if I use theta equals omega t for Earth or for Jupiter, theta equals Jupiter's angular velocity, I'll take it as omega j into t. Okay. For Earth, if I use it, listen carefully. For the Earth, the theta is 2 pi plus theta. Earth's angular displacement is 2 pi plus theta. It has gone 2 pi and then a theta. Okay, that is equal to omega of Earth into t. The t is the same for both. Both have been traveling for the same amount of time.
So why 2 pi theta?
2 pi plus theta. Now I told you the Earth travels one whole circle, means it has made already an angular displacement of 2 pi. On top of that, another theta. So the angular displacement made by the Earth is 2 pi plus theta. Isn't it?
Yes, sir.
So now I have two simultaneous equations. Theta is an unknown, t is an unknown. T is what we want. No, t is what we want. After how long does this happen? So easily, the simplest thing to do is I will subtract the two equations. I'll take this equation to be the first, this to be the second. Second equation minus the first equation will give us 2 pi plus theta minus theta is 2 pi. Omega Earth t minus omega jt. Okay. So 2 pi omega t, if I take it out, t times omega Earth minus omega Jupiter. Correct? So t is going to be 2 pi over omega Earth minus omega Jupiter. Am I right? Agreed? So what is this omega Earth minus omega Jupiter? Omega is given by 2 pi over t. So the omega Earth will be, in terms of months, radians per month, 2 pi over 12. Omega Jupiter will be 2 pi over 142.3. So omega Earth minus omega Jupiter will be omega E minus omega J will be 2 pi over 12 minus 2 pi over 142.3. Correct? So I will take 2 pi over 12 minus 2 pi over 142.3 is 0.4794. This is I'm taking in months. I didn't use a conversion. This omega is radians per month. Don't forget that. Because I know I need the final answer in months. So that's going to be 2 pi over 0.4794. So 2 pi over, that is exactly 13.1 months. Correct. 13.1 months. So the statement is what? The website states that the Earth and the Jupiter are in opposition. That means they are in line after 13 months. We are getting 13.1 months perfectly fine. Okay. Yeah, take it down. I'll explain it again. Okay, right. I repeat. So now let's say, guys, now this is a 5 mark. I agree that not a very straightforward question. Okay. But for a person who understood the previous part, t square is proportional to r cube, you can easily get this one and get about 2 marks. I don't know whether 1 or 2, but you will get that mark. You should be able to get that mark. T square is proportional to r cube, no? So time period of the Earth is 12. 12 square is proportional to its radius is 1.5 into 10 to the power 11, that cube. And time period of the Jupiter, if I take it as Tj, T Jupiter, Tj square is its distance from the sun is 7.8 into 10 to the power 11, that cube. By dividing these two proportionalities, it becomes an equation, and I get the Tj subjected, which is 142.3 marks. Okay. Agreed. Now, the only critical point that you need to think is it's also not a big deal if you, small thing, guys. Now, the Earth is traveling much faster around the sun comparing to Jupiter. Where Earth completes cycle in 12 months, Jupiter takes 142 months. No? Correct? So while Jupiter is completing one round, Earth has completed more than 11 rounds. So what I told is, now Jupiter is moving very slowly now. Jupiter is moving extremely slowly. By the time the Jupiter is moving from here to here, Earth has already completed one round, and in the second round, Earth has come to that line. Okay, so during this time period, if you look at the displacement that they have made, if you consider the Jupiter's time displacement to be theta, Earth has made a displacement 1 round plus theta. No? 1 round means 2 pi, right, in radians. So that means the Earth's displacement is 2 pi plus theta. So that is what I have done here. Used theta equals omega t. Angular displacement into time is angular speed, angular velocity into time is angular displacement. For Jupiter, if I use it, theta equals omega Jupiter into t. The angular displacement, angular velocities are different. Omega j into t. Earth, if I use it, the theta will be 2 pi plus theta. For the Earth, the angular displacement is 2 pi more than that of Jupiter. That is equal to omega Earth into t. Correct? The t is the same. they have been traveling for the same time. Correct? The t is what we need to find. So I subtracted the second equation minus the first equation. So the theta and theta will cancel off. So 2 pi equals omega et minus omega jt. So t is a common factor, I took it out. T times omega e minus omega j. So t equals 2 pi divided by omega e minus omega j. Then I got the omega e and omega j here and got the omega e minus omega j separately. Omega e is 2 pi over the time period of the Earth, which is 12 months. Omega j is 2 pi over 142.3. That is the time period of the Jupiter. So I didn't go to convert these months into seconds because anyway I know the final answer is required in months. So I got the omega in radians per month here. Then omega e minus omega j I got here in radians per month. Got that value and substituted here for the t. Then I'm getting the t in months. Understood. Is that clear? Right. You can go for a small break. See you in 15 minutes. And guys, after the break, start question 36 on page 63. Back to business. Right, there's question 36. In the 17th century, Kepler proposed his law of harmonies for planetary motion. This law suggested that the ratio of the square of the orbital period t to the cube of the mean radius r has the same value for all planets that orbit the sun. Mathematically, his law of harmonies can be written as t square equals kr cube. This is what we proved in the previous question, where k is a constant. The table shows data for the Earth and Mars. Show that the Earth and for Mars, k has a value of about this much. So guys, t square equals kr cube means k equals t square over r cube. So if I use it for Earth, k equals for Earth 3.16 into 10 to the power 7 square divided by the radius of the Earth is 1.5 into 10 to the power 11 cube. Similarly for Mars, k is 5.93 into 10 to the power 7 square over 2.28 into 10 to the power 11 cube.
Excuse me, sir.
It is for Earth it is 2.96 10 to the power minus 19. For Mars it is 2.97 into 10 to the power minus 19. So which is about 3 into 10 to the power minus 19. B. Kepler's law of harmonies was derived later by Newton. Newton applied his law of gravitation to a planet moving in an approximately circular orbit around the sun. Determine the value for K by applying Newton's law of gravitation to a planet of mass M moving in a circular orbit around the sun. Mass of the sun is given. So guys, once again, this is the third time we are doing it for the day. We use F equals ma for the planet which is orbiting around the sun. F is gmm over r square. M into A is r omega square. So the simple limbs, the mass of the planet will cancel off. Gm equals r square into r cube. R square into r is r cube. Omega square, I will write it as 2 pi over t square. So Gm equals r cube 4 pi square over t square. So the equation is in the form of t square equals kr cube, right? So if I get the t square subjected, t square equals 4 pi square over gm into r cube. So this is what Kepler has called the k. T square equals kr cube. So the question is to determine the value of k. So k is going to be 4 pi square over g. That is 4 pi square over 6.67 into 10 to the power minus 11 into the mass of the sun is 1.99 into 10 to the power 30. That's 2.97 into 10 to the power minus 11. This is the k according to Newton. Right, guys, I'll give you a couple of minutes. Quickly give me the answer to C. You're getting 42.6. Simple maths. E square equals KR cube. Yeah. So if you use it for one moon, which is having an orbital period of 172 hours and a radius of 1.07 into 10 to the power 9, 172 square is equal to K into 1.07 into 10 to the power 9 cube. For the other moon, which is orbiting Jupiter, the time period is T1, so T1 square is equal to K times radius is 4.22 into 10 to the power 8, that cube. So divide the two equations, second equation divided by the first, K will cancel off, you get the answer. Correct? Am I right? You don't need any physics for this, simple maths. O-level maths. Can we move on to the next? Right, guys. Can you mark a few for homework? 40. There's 46. We have only done the part D. Complete 46. 47. $53. $57. Yeah. That will be the questions for homework. Right. Now take the today's tube that I have given you. Theory tube, which is the note from the textbook. I have taken the part what is necessary for you and given it to you in this astronomy and cosmology. Okay, right. Guys, to begin with, now there should be a small idea that you should be having. Unfortunately, some of you don't have because you haven't done it for O-levels. From where you will get this? So, in O-levels, you learn about this. A little bit of astrophysics we have done. Listen to me. It's a very interesting topic. Okay, for me, I believe it will be the same with you. Something that we learn about beyond our Earth. Okay, it's a very interesting topic. Now, guys, if you see how old is this world? How old is the world? 13 billion years. Okay, fine. Now we are living in to my understanding, in a technically very advanced world compared to the history. Okay. So the technical advancement that we have seen in the last 50 years is, as a percentage, I would say more than the technical advancement the world had seen all put together millions of years back. Do you agree with me? Yes. The technical advancement the world has seen in the last 50 years is, as a percentage, way more than the technical advancement the world had seen before that. Millions of years I'm talking. Okay. So now in this topic now, back then, there are different books based on their understanding on those eras, whatever they have understood about the universe they have written. Or maybe there are some religious beliefs, or maybe there are certain religious teachings about the universe. Okay, so I'm not going to talk anything about those. Different people have different beliefs. Okay, you can have it, no problem. So I'm going to talk here in this topic, the science perspective. Okay, according to science, what is universe? Okay, what was it? Where was it? How did it start? How will it end? How will it go? That is what we are going to speak here. Okay? Understand? Fine. So guys, now you know this universe began with, okay, what is universe now? What is, we are in Sri Lanka. Sri Lanka is on Earth. Where is Earth? In the solar system. Where is the solar system? In our galaxy Milky Way. Okay? So guys, this galaxy Milky Way, who is the boss of this galaxy? Sun is the boss of this galaxy. Correct? I mean, in our solar system, Sun is the boss. So now if you take in the galaxy, okay, in our galaxy, there is a solar system and how the sun, the earth, and planets. There are millions of galaxies like this. Am I right? There are millions of galaxies. So all these millions of galaxies put together is what you call the universe. Okay? All these millions of galaxies put together is what you call the universe. So now, you know, from the O levels, so then if universe is expanding. Universe is expanding. How do we know? There is proof for the universe expansion. So what is the proof? One proof that is the most obvious proof that is available is the redshift. Have you heard about redshift? No. You haven't heard about redshift? Okay. You know Doppler's effect? You know Doppler's effect, right? So what is Doppler's effect? Now, when a source of wave is moving towards us, okay, the observed frequency is more than the actual frequency. Then the observed wavelength is less than the actual wavelength. That is when a source is moving towards us. So if a source is moving away from us, the observed frequency is less than the actual frequency. And the observed wavelength is more than the actual wavelength. Am I right? That is Doppler's effect in simple. So guys, now what is the evidence available that the universe is expanding? Now if you take the light which is coming from the other galaxies to the Earth, to this galaxy, to us, the wavelength that is observed is more than the actual wavelength. Okay? The wavelength that is observed is more than the actual wavelength. That means the wavelength is, if you take the natural visible light spectrum, red, orange, yellow, green, blue, indigo, violet. Red has the highest wavelength. So the whatever the color that is coming from that galaxy, from another galaxy, is shifted towards red, shifted towards a higher wavelength. So that is what you call a red shift. Okay, the wavelength that is coming towards us is more than what we observe is more than the actual wavelength. No, that is actual wavelength is from in the lab. You can compare the same colors. The laboratory, what is the color and what is that color? for the same color, what is the wavelength that we are getting and what is the actual wavelength that you can compare. So when you do that, the wavelength that we are observing is more than the actual wavelength, which is shifted towards the red. That is what you call a redshift. There is a clear evidence available that galaxy is moving away from us. Okay, the galaxy is moving away from us. And also in this topic later, we will be learning that further they are moving away from us, faster they are moving. Further they are moving, faster they are moving. So all this put together, it confirms that the universe is expanding. Blue shift means it's other way around, shifted towards a blue end.
It's like process.
That is in between two galaxies. There are rare cases. One galaxy is moving towards the other one. Then for those two galaxies, it will be like it's a blue shift. So if you just take those two, they are moving towards each other. But in general, if you speak about the millions of galaxies that I'm talking about, they are moving away from each other. Okay, right. So the universe is expanding. So which means if it is expanding now and based on the evidence available, that means all these galaxies started from one point. Correct? All these galaxies started from one point. And that point, there was an explosion. That's where the universe began. That is the theory, according to science. And that is what you call what? That explosion is known as what? Big Bang. The explosion is known as Big Bang. And then when did that happen? It's about 14 billion years ago. How do you know it's 14 billion years ago? Towards the end of this topic, we will be doing a small calculation, which will show, yes, the universe is about 14 billion years old. Understand? Then the question comes, what was there before the 14 billion years ago? That's my question. Okay? The
Nothing.
universe began 14 billion years ago. Okay, 100 years before that, what happened? That is not necessary for you also. I mean, not necessary within the syllabus. So we speak in science, what happened from Big Bang. So what happened before Big Bang, I don't know. I'm also interested to know, but there's no science which speaks about it. Okay, fine. So let me stick to the syllabus. So this is the background you need to know. Right. So guys, let's start with the topic. First page. And also, yes, one more thing that you need to know. That if you take a sun, if you take a star, okay, what is moon and what is star? What is moon and what is sun? What is the difference between moon and sun? Sun is a star. Sun is a star. What makes sun a star? Its performance. What makes sun
No,
a
sir,
star?
we draw it and also we like the stars, we draw that like triangles and all, right? So that makes it a star.
What? What I
No, it's nothing. It's a big ball of explosion, right? So just like a star.
it's like a Saudi joke or something.
No, sir, no, sir.
This is star. I used to draw this when I was in grade 2. Listen. So guys, the sun is a star now. And what makes it a star? It can produce its own light. Moon can't do it. Moon just reflects the light which is falling on it from the sun. So moon is moon. And sun is a star. Now if you take a star, from where did this star come? It is once again, after the Big Bang, guys, all these particles started moving away. No? Okay, so after that, there were gases, there were particles, okay. So due to this Newton's law of gravity, according to Newton's law of gravity, particles started attracting. They started attracting, and they formed objects. Those objects later on turned out to be planets and stars and moons and whatever it formed. So my point is, now if you take a star, it has a life cycle. It has a life cycle. So for an example, if you take our sun, it has a life period. how many years? Huh? It has a life period. So now we are actually, now how old is the sun? Is our solar system is how old? No, 13, 14 billion years is since the Big Bang. That is the commencement of the universe. I'm talking about when did this solar system was put up? How old do you think? It's around 4.5 billion years. Okay, so immediately after the Big Bang, the sun was not there. It took about 9 to 10 billion years for this to be formed. 9 to 10 billion years. Billion years. Okay, for it to form. So after the formation of this solar system, now it has been about 4.5 billion years. So actually we are in the mid stage of the sun. Okay, which is, I mean, if you can just try to go through this O-level textbook, you will be able to find these things. Okay, the sun has a life cycle about 10 billion years. From that, we have spent about 4.5 billion years, which is the sun is now in this main sequence state. Okay, main sequence state. So now, in a sun, when a star is formed, what happens is nuclear fusion takes place. What nuclear fusion takes place within the sun? Sorry, not fission. Nuclear fusion, what happens? Hydrogen. Hydrogen fusion happens. Hydrogen fuse together and form helium. And also the gravitational attraction takes place within the sun. So gravitational attraction will try to make the sun compressed, try to bring the particles close together. And due to the nuclear fusion which is taking place, will try to expand the sun. So we are in a stage where this outward force and the inward force are equal. Currently that outward force and inward force are equal. Forces are equal. So that is what you call the main sequence of a star. So the sun is actually now at the moment in the main sequence. There are certain stars which have gone passing the main sequence. They are about to die. Okay, they will be. What will happen to that after dying is there's another cycle, which is not necessary, but you have done it for O levels. Those who have done edX at O levels, definitely you have gone through this. You have learned this. What will happen to a star? What will happen at the end of it? How is this formed? Okay, what is a white dwarf? What is a planetary nebula? You have done these for O levels. If anyone drop me a message in the WhatsApp group, I will send you a detail, small document before the next class. Read that and come, which is the O-level textbook document. Just read it and come. That will give you some idea about the background of it. Okay, fine. Page 1, stellar properties. Stars are at such large distances from the Earth that the only information we have about them is the electromagnetic radiation we receive from them. However, from this limited information, we can measure various stellar properties. Okay. These allow us to classify stars into various groups, which have quite strange names, such as red giants, white dwarf, and blue supergiant. They are much too far away from us to spin probes to them, or even to send signals to them in the hope of detecting reflections. However, scientists have managed to determine a large amount of detailed information from even the faintest glows in the night sky. Incredibly, the electromagnetic spectrum from stars can tell us their temperature, chemical composition, speed of movement, approximation age, size, and much more. Okay, from the electromagnetic spectrum that we are getting from the stars, we can determine all these details: temperature, chemical composition, speed of movement, approximate age, and size, and all these details can be taken from the electromagnetic spectrum that you are receiving from them. and black body radiation. A black body radiator is a theoretical body which completely absorbs all radiation that lands on it. Okay, there is a black body. Now guys, on a surface, usually when light falls onto a surface, why you can see me is, okay, why you can see me is, whatever the light falling on me is reflecting, and that reflected light is passing through your eyes. So your eye will send a signal to your brain. So the brain is not reading me. Am I right?
So there's a paint a guy made, like the blackest of black paint. It's like that, like no light reflects at all.
What?
A guy
Black?
made the darkest black color, the darkest black paint.
You
Yeah,
can still see it, is it?
No, you can't. Light doesn't reflect it.
Here I am showing you some black paint. Can you see? Can you see?
No.
Wait, that is too advanced for him, I think. We can imagine. Listen, guys. So what is a black body? That is something which absorbs. Oh, wait. Which absorbs all the light which is falling on. Okay, which absorbs all the light that is falling on it. So it doesn't reflect. Okay, so if it doesn't reflect, you can't see it. Yeah, so if you are to see it, it has to reflect the light. Whatever it is falling on it, it absorbs, means you can't see it, right? Anyway, have you heard of this black hole? You know what is a black hole? What is it? It is a hole which is black, is it? So there's black hole is, listen, it is if you take a star which is a massive star, the end result of a star at the end of its life period, it will become a black hole. I will stop the day with that. An interesting fact, okay? It can absorb anything that goes into it. It can absorb anything which goes into it. Listen. Yeah, listen. You know, the earth which is, just for you to have an understanding about this, I read recently. Earth which is having a radius of 6,400 kilometers, diameter of 12,800 kilometers. Okay? If this is sucked by the black hole, if the earth is sucked by the black hole, earth will become a cube of 1 cubic centimeter. This earth, which has a radius of 6,400 kilometers, if it is absorbed by the black hole, it will become a cube of 1 cubic centimeter. So that means the gravitational field there is extremely high. It can compress the object, the entire earth, to 1 cubic centimeter. Fine. So we'll continue from here on the next day. Please bring the tube for the next class. That's it for the day. Bye. See you again. Yeah. What was your question?